Over several centuries, the study of light and its interaction with matter has been crucial in the development of technologies leading to our modern society. Most of these developments are also helping to uncover details of the nanoscale world. Light usually interacts with objects at least as big as its wavelength, which is around 500 nanometers for visible light. The nanoscale world is much smaller than this, and yet it can still affect light. Developments in nanoscale science mean that we can now manipulate light in ways never before anticipated. Metamaterials can now be designed that have specific properties and can alter the electric and magnetic fields of light in unique ways. For instance, the recent developments of invisibility cloaks in the infrared and microwave regions has been due to designing structures for materials that bend the electromagnetic radiation in unusual ways. Light is another form of electromagnetic wave, and designs for invisibility devices for visible light have been developed, though not yet made. Some of the other nanoscale devices of interest would be quantum dots, which are two-dimensional nanoscale structures that can be used to make lasers, or they can be built into solar panels to make them more efficient. Negative index of refraction materials are also a new type of metamaterial. Many new applications of nanoscale structures for the manipulation of light are being developed all of the time. The specialized equipment of the optics lab is used to train students in how to deal with optical systems and allow them to analyze nanoscale materials effectively. They will be able to gain insights into an emerging field called nanophotonics. A scanning tunneling microscope, or STM, is an apparatus similar to an atomic force microscope. It uses a fine needle point, roughly 1 to 10 atoms across, to image a surface of a material. The basic principle behind the STM is quantum tunneling, a process whereby a particle without the energy to classically pass through a region is allowed to do so under very specific constraints. The material being examined must be a conductor, like a metal or a semiconductor. There's a gap between the surface and the tip, and electrons have to jump from the surface to the STM tip, or vice versa, depending on the microscope arrangement. The closer the tip is to the surface, the easier it is for the electrons to jump and a bigger electric current flows. By moving the tip across the surface and monitoring the current flowing through the circuit, a detailed image of the surface can be reconstructed with a computer. The structures on the surface can be as small as between 1 and 10 atoms across, making the STM a very powerful nanoscope.